master. We'll do everything inline and we'll do a global string lock. Alright, so that's our order of operations. Basically, we do our call, check our stat leaderboard, do a string lock on the thing, check our stat leaderboard again, check memcache, query the database, create the leaderboard locally after getting our answer, populate the local cache, write to memcache, and then unlock our string. So that's what we need to write in code. So this fetch stat leaderboard, we probably want to create a leaderboard data structure here. Our leaderboard data structure is going to be our user stat history. Let's make a new class here with data structures. Alright, so if we got a stat leaderboard, we're going to want to do, we want like in created time, we're going to want string, which will be our stat context. Interval ID. We'll need our stat name. Stat context interval ID, so that's going to be online, week 5 goals, top 200 people. Alright. Then we're going to want the user stat history array, so we need the actual stats. And I think we also want the stat interval. Alright, and this class needs to be marked up. So we can store it in JSON. So basically what we're going to want to do here is we've got a stat leaderboard, so it'll be get leaderboard for this. So we'll return a leaderboard. We do not have a top number because we're just going to max it out. So this call is going to do all this stuff. So do I have a string lock thing made? I mean, I could just use a lock container. Probably the best way to do this. So let's go ahead and boot up our leaderboard locker. And let's give like a max locks. Let's give it 400 locks. All right, and the other thing that we're going to need to do is we've got a concurrent hash map. Okay, so what we're wanting to do is we want to snag the stat leaderboard from this guy. So leaderboard. So if leaderboard equals null or now minus leaderboard created time is greater than our max created. So I can go put these off into config vars later. Why the fuck do we even have memcache on this? Like, because it could solve a few problems. I mean, they basically need to be the same, don't they? Otherwise, there is absolutely no point in memcache, because we're just going to be like, oh, well, it's too old anyway. So let me just invert this. So created time, now minus created time is less than this time, then we just return our leaderboard. So it was a trivial case. We already have the leaderboard and it's already good enough for us. Get loader board? Alright, yeah, leaderboard. Otherwise, we need to get our lock. So let's lock this thing. Then let's go ahead and get our leaderboard again. So we'll do check lock check. If you're not familiar with check lock check for threading, basically the idea is, like, let's say you wanted to do exactly this. Basically what you do is you check the answer to see if it's available. Then, like, let's say you have a config system or something and you want to fetch something. Basically, you check if the answer is available. If the answer is available, you just return it. Otherwise, you lock. Then you check it again, and if it's available, you return without an unlock. Otherwise, you hold on to the lock, load it, and return. And then basically what will happen is, usually if this is an expensive operation, you'll have a lot of threads waiting with check lock check if the answer isn't available, but none of those threads will be like consuming CPU and like slamming your database. Only one of those threads is actually going to go load that external resource, and then everything else will just return and then just get executed immediately. So it's, just tick, 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 tick. It'll work. So check log check is kind of the way to go for a lot of threading problems that you might have. It's especially good for singletons, where you have like a thread come in and try to grab a resource that only gets loaded very, very, not very often at all, because basically check lock check then will have, no impact on your systems. Well, it's not cache busting. Check lock check is just a pattern to use when doing like a cache bust. We're going to actually need the database, the cache. Do we have a cache? Like, we have globals, but we've got game database wrapper. We have our auth cache wrapper. But what we're going to do is have like our stat cache. So I need to edit the configs for this stuff to add a stat cache. Well, we have a game cache. Yeah, okay, so why don't we just use the game cache? That'll work fine. Alright, so context will give us this thing. So memcache is like a real simple cache in and of itself. So it's just key value binary blob stuff. So I always prefix this stuff with like a server context. So this is going to be like production, and then like .stat leaderboard, and then like the key or something. That way I can share memcache instances across environments without a problem. And this is helpful mainly because if you ever have some sort of configuration issue where your two different systems are using the same database on accident, you sometimes don't realize that if your security groups or whatever aren't set up properly. So let's say like you boot up your backend tools thing that like goes and makes and does a whole bunch of crap. And usually your backend tools can talk to almost everything because, you know, they kind of need to. And if you accidentally run something that goes to like the prod memcache or something and is over, you know, stomping on keys that you don't think, you know, like that you think that's your database, I don't know. A misconfiguration there can really fuck stuff up. So that's one of the things I've seen in the past. Okay, so we've loaded this thing from the cache. So if the leaderboard does not equal null and this cache bus time is, you know, everything's fine, then what we want to do is we want to insert that into our local. And then we want to return leaderboard. This cache leaderboard. And yeah, alright, thank you, warnings. Otherwise, we need to actually load this from the database, don't we? So we need to call Alright, so we're going to need to populate the interval. So we're going to want to first throw this into our leaderboard map. Then we're going to want to write this to memcache. Alright, so I'm not gonna like actually fail on this sort of thing. Okay, so for the intervals, this cache bust is totally like it is, so we need the interval ID. So should we just load the interval from the database, just straight up? I mean, we might as well, right? So if we don't have the interval, I don't want to fail this call if like something is screwed up. I just want to warn. So what I'm gonna do is we can just do like unknown. Maybe we should just fail it. Just like, yeah. Fuck it. If it's broken, like that's a big problem. So we should just break. All right, so that's going to go ahead and get our leaderboard for this thing. So if we want to cache leaderboards like every minute or something, what we could do is just have a thread running here which goes and fetches this stuff. Well, wouldn't be the worst thing in the world, right? Just to maybe have a warm cache thread that's not too hard to write since I just got this stuff running. All right, so what we're going to do is make our threads. So if anybody noticed, we made our running volatile because we're going to be editing this outside of our loop, and Java's kind of interesting in how its multi-threading optimization works sometimes. Basically what'll happen is, let's say you have a Boolean that this thread checks, because there is no thread stop. You can't just like stop another thread. You have to like signal an interrupt, which goes and like makes that thread do things and like check a variable to see if it should actually stop, and like all this other stuff. You can't just halt a thread because of how memory works and that sort of stuff. It's actually a fundamental problem. But what'll basically happen is Java doesn't actually compile its code into, like, it doesn't actually optimize its code all the time. It's called the hotspot JVM for a reason. Basically, the JVM will optimize bits of code based on how hot that code is. So you won't see concurrency issues unless you actually have like a thread that is actually hot. So you might be writing code that is, the optimizer will actually optimize wrong for your threads, but it runs just fine in all your systems across like all your services because you've never actually written a tight loop in a thread that actually made the optimizer go in and do that. So a lot of people have a lot of bad habits with threading in Java, mainly because they've never actually written something that the optimizer went in and did. So they're like, well, I've coded this way forever and it's always worked. Why is it, what do you mean it's wrong? So you gotta watch out for that, which is like volatile variables in JVM land basically says don't optimize the read of this. So if you have a thread that's checking like a Boolean, make sure it's volatile. That's actually one of the more common things that people mess up. Another thing here is that if you're noticing how I'm organizing my exceptions here for this guy, basically we have while running, do our update, and then regardless of an error, do our does, and then you have a try catch outside of that. So it's like, well, why do you have a try catch for the update and then have a try catch for the loop? Well, the issue is a lot of times what'll happen with people's code with threading is they'll have a thread here that's supposed to run and do stuff, and as soon as it has a problem, it triggers an exception. So it would like jump up here. So if I put the does, for like my sleep, for like wait around a little while, right after my update inline, and there was like an exception inside of here, and it might be a simple exception, such as like a null or something that's not actually specifically declared. So you might not, it might be an out of memory, it might be anything. So if you don't always have your sleeps with like these protections, what'll happen is as soon as an error happens, it will skip the sleep in its tight loop. And all of a sudden this thing that's supposed to run every 30 seconds just runs right after itself. And as soon as there's an error on the server, well, it's probably going to have the same error immediately. Like if a service goes offline, like an external e-commerce server or something goes offline or stops responding, right? Even worse. So you have a service that is overloaded, and then you have another service that calls it to get information every so often. What'll happen is if you have a bug, like the server gets overloaded, it'll come back and say, okay, there was an error. So your service, because you coded your loop wrong, is now going to immediately call back again, and this service is, still sick and screwed up. It's going to immediately hit it again. So all your backend servers start denial of service attacking the thing that is already overloaded. So it's little things, little practices with how you code servers turn into massive production issues if you don't realize what the fuck you're doing. The other thing you might be wondering is why I am not doing the config check for even creating the thread, and it's because we hot reload stuff. Anyway, the reason why I know all this crap is because every one of those things I talk about is something that has literally happened to me in production for some reason. Okay, so we want to fetch the common intervals. So what is that function? Fetch latest stat intervals. Alright, so we gotta fetch our common intervals. We need to get our common stat contexts. So that's going to be, I believe, our WD stat context. Let me take a look. Offline, online. And yeah, I'm just working on stuff. Okay, so for every stat context, and then we need for every stat name. And we need for every stat interval. So we got 3 loops. Well, if we got 3 loops, why not more loops, right? So as a result, we're going to need to call this dude. Okay, so we'll have it here that we can actually pass in a cached interval if we want, because we already have it here. So we need to call get leaderboard for. Stat context. So let's just do this. Thank you for following Robert3869. I hope you find my angry rants as entertaining as I do in my own head. So instead of, like, we already have these log spam things here, interval name, stat name. So basically we're just going to count up our errors and print this out, because this is going to be like 400 or whatever, you know, errors, right? So it's already going to tell us what's busted. The other thing we could do is if there is an error, we could just go ahead and stop. That's probably not the right plan. We should probably have like errors for stop. Bam, 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 bam. Alright, so that should reload all the stuff for us. Excellent. It's a lot of data. Okay, so if we've got 30 stats, two contexts, we got 6 intervals, we got 100 people. Maybe like 64 bytes. Alright, so 64 bytes per stat. We've got 30 stats times 100 people times 2 context. 6 intervals, so that is 2 megs. So our common leaderboard data is actually like 2 megs of information. Really? Shit. Well, not necessarily. Well, yeah, it kind of is. Because of all this. So... is that true? Let's do some math. So we have 6 active intervals. We've got 30 stats. We've got 100 users in the top whatever. We've got 2 contexts. We've got, for every one of these stats, the data structure for it is what? An array list of user stat history, which has got account ID, so let me think. I might want a condensed form of this. So like a user stat leaderboard. So it would have like the interval ID. No, it would have the stat interval. Stat context. The stat name. And then it would have user leaderboard stat, which would just have an account ID and then a stat value. And we would have stat values here, which would be a user leaderboard stat. So how big is this data structure going to be? It's going to be, so we have 6 active intervals, so we're going to have 6 of these times 300, so this is the interval size is going to be a stat interval, so it's going to be 64, 128, 192, like it's going to be, like I can just say 200 bytes. For 30 stats, the stat is going to be because I'm thinking about when we return this leaderboard to the client, even after we have it, like how much data are we actually sending back in our RPC call? Because if that's too big, then that's another massive issue, right? Like great, you cached all the information, but your app server is now serving out like 2 megabyte uncompressed answers to questions. Okay, cool. Well, I really hope you want to pay for all that frickin' bandwidth because you used a shitty data structure for it. Because at that point, you just put those damn things on S3 and just like your service is crap because. All right, so our leaderboard, we have a stat context that's going to be like maybe 30 bytes. We're going to have 100 users, which is going to be 32 bytes plus 4, so it's going to be like 40 bytes and 2 contexts. So we just do a times 2. Contexts are a 0 actually, so it's going to be 6 times 200 plus, no, I should just do 200 plus 30 plus 40 times 100. We're duplicating this thing. Okay. So it's going to be so we're going to have 4,000 bytes for every stat. So it'll be 4,000 plus 30 plus 200 multiplied by our thing. So it's going to be times 6 times 30 times 2. So it's going to be 4230 times 6 times 30 times 2. Really, that's all we got to cut off of it? So that's, you know, going to be it's going to be 1.4 megs. Okay, so if we cut this in half, so we have top 50 instead of top 100, we just get, you know, 1.4 goes down to 0.7. Well, darn. Looks like we're just going to have a 1.4 meg call. Well, it's not the worst thing in the world. We can see how it goes and if it's an issue. The issue is it's all frickin' encrypted. Should we just gzip the damn thing? But then I have to implement gzip on everything. Well, I can just trim it down. I mean, we could stop doing all the stats and all that. I can always just have the user specify the stats that we're going to send and just do that. Alright, why don't I do that? But this also, the user stat leaderboard data structure is a better data structure than I was returning before, so I should switch over to sending that back. So we'll save ourselves some data, and actually quite a bit of data. Chopped it into like 30% of what it was going to be, and it's also in a form that's useful, as opposed to just a raw exploded mass of numbers. It's like actually organized by interval and by stat, and the user IDs are all nice. So, because that's the other thing we got to worry about. We have to then pass all that information off to the UI to actually render. So you're passing a megabyte of data to be turned into a JavaScript object for the UI to read. It's really funny, like when you start dealing with large amounts of data like this, just normal day-to-day operations turn into an exercise in being very angry with yourself. I'm reading a story on Slack. Yeah, shit. Gummy raid. All right. Gummytainment. Thanks for sending people over. I'm stuck reading stuff.